So this is maximum power transfer for circuits 2. This is your third lab. And I'll let you know ahead of time, this is an easy lab to get confused on. So you want to pay attention to what you're doing. There's lots of little tricks. And make sure your multisim is worked out before you start any experiments, because this will indicate to you if you're off track or not. We'll want to refer back to our Thevenin lab, in which we took a circuit like this and transformed it into this, right? And we're going to utilize the fact that we can change this load now. In our Thevenin lab, we kept the load unchanged, right? So let me go back to essentially the idea of our Thevenin lab. We showed that we can take this network here, this circuit, transform it into this. And as far as the load is concerned, which the load remains unchanged, it's the same circuit. The voltage drop across it is the same before and after transformation, right? So that was Thevenin. And in order to get to our Z Thevenin, remember that we did a calculation for what our impedance should be, right? So it told us how much resistance we needed for our Z Thevenin and how much reactance we needed for our Z Thevenin. So we selected these components in order to provide that for us. But now we're going to do something with the load value, which is we're going to select the load value. We're going to change what this load value is, particularly the reactive element. So in our Thevenin equivalent lab, these were both maybe capacitors in your case, but in my case they were, but perhaps you had a inductor here and some other component here. But I'm going to select this component such that the reactance of Z Thevenin and Z load cancel each other. And this is what your lab is trying to point out here. It's talking about the fact that your Z load is the complex conjugate of Z Thevenin, right? So what happens when you do that? When you select this inductor value to cancel out this, you only have two resistors in series. And it kind of goes back to your circuits one days when you did the maximum power transfer and you varied this resistor value and you showed that when this resistor equals this resistor, that's when the maximum power transfer happens through the circuit. So let's go back here. Remember, we determined our Z Thevenin and we got a resistance and a reactance. Now, this is telling me what the reactance of my Z Thevenin element is. The complex conjugate just has the opposite sign here. It should be positive 44. So I'm going to select an inductor using my reactive inductance equation, which is 2 pi FL, that will provide me positive 44.8 or 9 or whatever it is. So I kind of rounded off some numbers, but this is the inductor value that I need at 1500 hertz in order to cancel out the reactance from this element. Now I'm going to use a trick here in Multisim. We may have used it before, I actually don't recall offhand. But what I'm doing here is a parameter sweep. When you actually do the lab physically, and I'll show you later, you have to vary this resistor value, and you'll probably use a potentiometer, or you could use a bunch of different resistors. And what you're going to do is you're going to switch the resistance value incrementally and collect your current. But here in Multisim, it's doing it all for me, right? So when you collect your current, you can use your equation to determine your power. So in the lab here, they provide the power equation, 1/2 I squared R, and that's the power consumed by this resistive element. But Multisim makes it a lot easier. I can just attach a power probe to this resistor and do what's called a parameter sweep. So there's a couple things to look out for here. First of all, I want to select my device type, which is my resistor, and the actual resistive element that I'm using, and this one is R1. The parameter that I'm changing is resistance, and it shows me the present value. Now here, this is the range of values that I'm going to probe over from 0 ohms to 200 ohms, and I'm going to do 50 points. It doesn't really matter, you can do whatever you want. The only thing to remember is that this is a nonlinear equation. So if you look at the graph provided in the lab, notice that this rate of change here is much higher prior to that peak, and then it kind of slows down, right? So when you're doing this experimentally, you may want to collect points closer together as you approach the maximum power transfer point, which is RL equals R thevenin, and then later on you can kind of space them out further. So you're probably going to collect maybe about, I don't know, 14, 15 points, and you should get a decent enough graph. So let's go back here. I've selected a range from 0 to 200, 50 points. The analysis is single frequency AC, and make sure that you selected your working frequency. Usually this starts up at 1 hertz, so you can hit auto detect. And the number format is magnitude and phase. Then I'm going to go to output and make sure that that probe that I placed on the resistor is the output. Okay, so let's run this and see what it shows here. So you can see a similar graph to what's shown in the lab, right? It's this nonlinear curve, and it rises up to some maximum. Now here in Multisim, I can go to cursor and show cursors, and I'm going to select go to next Y max, and my probe 1 automatically jumps to the point that is the highest on this graph here, and it shows that that point is at 53.1 ohms, right? Because it's being plotted here. And that makes sense. This is plotting power as a function of resistance, and the maximum power transfer happens roughly when this resistor equals this resistor. And that's all we're really looking to prove. The experimental portion is a little bit more complicated, and so I'm going to turn to that, and I'm going to show some LCR measurement values as well to validate it. One important thing to note here is that when I measured these values, of course I have some additional resistance from this inductor and from this capacitor, and my circuit looks very wonky. For my physical experiment, I actually had to use 5 different inductors in order to get roughly up to this value, and 4 capacitors to get roughly this value. But in the lab, you may have some more options for capacitors and inductors, and you can figure out exactly what you need to do in order to get here. I want to make one special note though, which is that you don't need to use your Thevenin equivalent circuit in order to create the load here that's going to cancel it out, because remember, these two circuits are equivalent, right? We already determined that. So if I was to place this load here into my original circuit to replace this load with the one that is tuned to cancel out the reactance, it will behave exactly the same. So if you are working with your original circuit that you use for your Thevenin equivalent circuit, you can do so. Just replace your Z load with the element that you determined you needed in order to cancel out the reactance. So you are not obligated to use the Thevenin equivalent circuit. You could use your original circuit because they behave exactly the same as far as the load is concerned. So I know that was a little long-winded, but there's lots of little tricks to this lab, and now I'll turn to the experiment, and hopefully that will resolve a lot of questions. Okay, so we're on the experimental portion for this lab, and let me explain my circuit here. These two elements combined, this resistor and this capacitor, compose my Z Thevenin. And this series of inductors and this potentiometer compose my load, right? And I chose a potentiometer because I can vary the value and then get a reading. Now you can just take, if you want, take 15 different resistor values and just put them in one at a time, measure the current through. That actually might be easier in some cases, so feel free to do that. I did add these 2 little leads here to the legs 1 and 2 on the potentiometer, so I can just get a resistance measurement very quickly and then go back to my circuit. And I'm working with just 1 multimeter, but in the lab you could use a couple so that you have 1 dedicated for resistance and 1 you can use for the current measurement. In any case, I had to put all of these capacitors in parallel because I'm trying to add them up to the value of 2.364 microfarad. What I actually ended up with when I measure it on the LCR meter is 2.27 microfarad. For the inductors, I wanted 4.78 millihenry, and actually I got that just about on the dot. But one important thing here to note is that all of these added inductors also increase the resistance of my circuit. So I measured that on the LCR meter, and I had an additional resistance of 9.5 ohms from these inductors, right? So it's a couple things here to think about. When I do a measurement, I basically always have to bear in mind that it's whatever I measure plus the value of the resistance from the inductors. But initially I'm going to ignore that. I'm just going to collect my resistance values, go incrementally 1 at a time. But later you can compensate for that and say, you know, I had an additional 9.5 ohms that I can't remove from the circuit, and so then all my values are shifted, right? So anyways, hopefully that suffices as an explanation. Let's get started here. Let me make a slight change here. So first, I want to simply measure my resistance value on my potentiometer. I connect the leg here and here. All right, and I have an Excel spreadsheet open. I'm going to type in 5.4, and now I'm going to switch to a current measurement. So I come here, switch to my function generator, and of course I changed all my parameters in my function generator already. So I have my thevenin equivalent circuit and my function generator is where it needs to be. And I connect the back side of here, negative side, to the front of my circuit. And what I'm going to use the oscilloscope for is to make sure that I'm actually getting the intended voltage. Okay, so this looks a little complicated here. So I needed, according to my thevenin, I actually needed about, what was it, 1.52 or 1.53 volts. So let me shift this a little bit until I have 1.53. And remember, because I'm constantly changing the load value on the resistor, I have to keep an eye on the oscilloscope and make sure that I always have my intended voltage going across. I'm not going to keep doing a load compensation on the function generator. I'm just going to look at what this value is. And here I want 1.53. Okay, and there we have our current measurement. So I'm going to type that in, 7.88 milliamps RMS. Okay, go back here. We're going to switch to a current resistance measurement again. Take this probe, put it here. So this is very tedious, I understand, but in the lab, like I mentioned, you will have 2 resistance measurements. So now it's measuring resistance, and I'm going to take my potentiometer and slightly increase the value here. No. So as I'm turning, and you can always add data points afterwards. It doesn't really matter where you do it. If your graph looks a little sparse afterwards, feel free to add a data point in between. So now I have 16.1. I typed it into a column on my Excel spreadsheet. And let's go back. So So now we have to go back to this setup, function generator, switch to a current measurement, go here, this whole rigmarole. Okay, we're back. And what did I misconnect? It can happen. Oh, just didn't have my multimeter slightly clicked in. Again, I have to adjust the voltage here to 1.53. And measure this, so 6.81 milliamps RMS. Of course, your current is always going down, right? As you increase the resistance, your current can only go down. But your power equation says 1/2 I squared R is the way you determine the power through the resistor. So that's that will not continue to go down. So what I'm going to do is I'm going to collect a number of more points. I don't have to show you this, but you kind of get the process. Feel free to gloss over it. I'll do one more point at least. And okay, so I turn off the function generator. I go back here. I do resistance again. And again, hopefully you're a little faster than I am. And I'm going to go ahead and increase that again. I'm going to go up to whatever it is, 25.2. And now we go back. Switch this over. Make the adjustment again. Okay. 6.1. All right. Yeah, that's enough. I'm going to collect a series of measurements, and then I'll show you my Excel spreadsheet afterwards, and we'll talk a little bit more about it. Okay, so now we are in the plotting part. I collected a series of measurements for these resistance values, and I simply noted down my currents, converted it to amps, and then calculated power in Excel, and then I plot that here, right? I have power in that resistive element as a function of its resistance. And notice that I kind of spaced these out much further as I got along here, because this is going to change very gradually. And I'm just using a scatter plot, and it does this kind of interpolation, or it just draws a line through the points. And so I don't bother to do a bunch of tiny little incremental points around where the peak is happening. I just kind of do it way further out. But this is offset from what I expected, right? The peak is probably happening somewhere in this range, and I expected it to be, in 53 or so somewhere here. So it's roughly the same, but it's a little bit different. And one explanation for that, possibly, is that I can't exactly cancel out my reactance as I do in multisim. So I mentioned that here in multisim, I have my perfect ideal resistors and capacitors and inductors. And but when I actually measured my values on the LCR meter using my real physical circuit, I still had some reactance left over, and it was negative 3.6 ohms of reactance. So we expect to get some offset. And in addition, the resistance from the inductor, that's going to create a little bit of some issues with the data set, but overall this is pretty good. We can live with this. Really what we want to see for your lab is just that you can generate this general curve and get the maximum power, in the neighborhood of. And again, don't spend too much time making small little incremental points here. kind of collect more points right around the peak and then start spacing it out further. You can extend this line further out if you want, but you can kind of see the general trend is going down. It's just going down very gradually. So hopefully that helps you in Lab 3, and I'll see you on Wednesday.